To build the next massive wave of human industry, we have to solve a physics problem. Right now, human progress is bottlenecked by the laws of thermodynamics and the gravitational pull of Earth. The mechanical recovery of a 20-story rocket booster serves a functional purpose beyond its visual impact. It is the specific mechanism designed to bypass those physical bottlenecks. This chart maps the historical cost of moving physical matter into low Earth orbit. During the Space Shuttle era, launching a single kilogram cost roughly $54,000. By achieving rapid reusability, SpaceX's Starship is designed to drop that target cost to around $10 per kilogram. A 99% reduction in transit cost makes high-volume orbital manufacturing business models mathematically viable for the first time. For 60 years, the reason to go to space was scientific research. Now, the reason to go is to manufacture high-margin physical products at scale. Affordable access to orbit turns space from an exclusive government program into a commercial industrial zone. Every time you double the total production volume of a technology, the cost drops by a predictable percentage. Economists call this Wright's law, and history shows exactly how this math plays out in the real world. In 1956, global trade relied on dock workers manually hauling individual barrels in crates. The standardized metal shipping container collapsed that transit cost by 97%, allowing countries like South Korea and Vietnam to build entire export-driven economies on that single invention. 40 years later, the cost of transmitting data through optical cables dropped by a factor of 1,000. Streaming a movie in 1995 over dial-up would have cost hundreds of dollars in bandwidth. By 2015, that identical data transfer cost fractions of a penny, allowing the modern digital economy to exist. Starship is applying that exact mathematical cost curve to rockets. It acts as the standardized shipping container for moving physical mass off the planet. When the cost to move matter or data drops by over 99%, trillion-dollar industries emerge that no one could predict before the price collapsed. The first industry moving to orbit is computing, specifically artificial intelligence data centers powered continuously by the sun. On Earth, AI data centers are hitting hard physical limits. They require enormous amounts of grid electricity and massive amounts of water for cooling. In orbit, solar panels provide uninterrupted energy, and the near-perfect vacuum of space allows chips to radiate thermal heat directly into the cosmos. Major tech leaders are already preparing for this. NVIDIA recently announced the Vera Rubin Space One, an AI chip delivering computing performance 25 times higher than previous orbital processors. The second major sector relocating is zero-gravity manufacturing for pharmaceuticals and semiconductors. Removing the downward pull of Earth's gravity allows molecules to align in perfect, unbroken crystal structures. Microgravity environments allow crystals to form with virtually zero defects, significantly improving the yield of semiconductor wafers and complex drug compounds. Direct thermal radiation into the cosmos, continuous solar exposure, and the lack of a gravitational pull provide the physical drivers for off-world profit. These factors solve the industrial limitations hard-coded into Earth's environment. Launching the raw materials is only half the equation. You still need a massive labor force to build and maintain these orbital data centers and factories. While human spaceflight has been romanticized for decades, from a strictly economic perspective, human biology is a massive liability in orbit. A human body requires constant oxygen, water, food, and heavy radiation shielding. Maintaining the infrastructure required to keep a small crew alive on the International Space Station costs hundreds of millions of dollars per year. The economic solution is automated labor. Millions of mass-manufactured humanoid robots require no life support, no sleep cycles, and no protection from cosmic radiation. This chart compares the daily operational expense of biology versus automation. Supporting an astronaut costs roughly $1.4 million a day. By comparison, operating a mass-produced humanoid robot in space drops the effective labor cost to around $2 per hour. At $2 an hour, orbital machines can work 24 hours a day, performing continuous construction in conditions that would kill a human in minutes. Building a multi-trillion-dollar off-world economy requires evicting human biology from the supply chain. The final industrial zone will be almost entirely automated. We are moving toward a reality where orbital networks connect a sprawling system of automated solar factories, data centers, and mining drones. built and operated by machines. The greatest financial returns lie in the second and third order effects, the unpredictable industries that emerge after the core infrastructure is established. Just as the inventors of the shipping container could not foresee modern global e-commerce, today's engineers cannot map out every industry that will result from cheap, reliable access to orbit. This transition is actively underway. Billions of dollars in private capital are flowing into these companies, and the foundational hardware is launching right now. The mechanical recovery of a heavy lift booster serves as the physical architecture for moving heavy industrial production off-world, securing an economic future that is currently difficult to quantify.